Webinar today. Okay. Yeah. Well, let me start again. The recording started. Hello, everyone. Thank you so much for joining this Rising Star webinar today. My name is Allie Yamagata from Saint-Gobain and Secretary for the Cements Division, and I'll be your host for today's webinar. Before we start, I want to share a few highlights from our division. We want to thank everyone who attended the 16th Advance of Cement-Based Materials. We had amazing talks, poster session, networking event, boat trip, industry pitches. It was really good. And on behalf of the cement division, I would like to thank all the sponsors of the conference. Thank you for all of them. All this was possible thanks to the sponsors. Next year, the 16th Advanced of Cement-Based Materials will be in Virginia Tech, so make sure you attend this event in summer, and we will be sharing more information. Please consider sponsoring it. For those who are not familiar with ACerS, being a member of ACerS gives you access to resources that allow you to continue to learn and grow, gain recognitions with awards and scholarships. One of my favorite things is the mentorship program for faculty, industry, and also students. The 2027 ACerS mentorship program application will be open in October. So please make sure you sign up for that. This webinar was brought to you by the Cements Divisions, one of the 11 divisions of the American Society, and we're dedicated to advancing the fundamental material science of cementitious material. There is many things for you, opportunities to connect, meeting, events, resources, leadership, development, opportunities, awards. It gives you access to peer-reviewed journals. And by the way, our special issue, Emerging Cement Chemistry, is already available online. Please check it out. Thank you for our guest editors, Pranay Surnami, Shihokawa Shimen, and Alexander Brandt. So now it's my pleasure to introduce Professor Franco Zunino, Assistant Professor at the University of California, Berkeley, and a leading research in low carbon cement and supplementary cementitious materials. His work has received international recognition through several prestigious awards and leadership roles in ACI, ACM, and Riling. We will have a Q&A session after this talk, so please stay on. So Professor Zunino, thank you so much for joining us today, and it's a great honor to give you the floor.
Thank you, Ali, for the kind introduction. I'm very happy to be here and to be joining this notorious series of seminars that the Cements Division organize for our community. And the goal of my talk this morning is, in a sense, to show some of the things that we have been working on, some of the things that we have been thinking about. But more importantly, and I think that the title evokes that intent, is to provoke thought and to provoke critical approaches in the way that we characterize our materials, and particularly in the context of the ongoing challenge of decarbonization of the cement and the concrete industry, that from a cement chemistry point of view is likely introducing the biggest change in this particular domain since inception, right? Like the adoption of all of these supplementary cementitious materials is changing the chemistry of the system. And there is a lot of things that we now need to understand better and consider in order to effectively use these resources to achieve our decarbonization goals, as I was saying, but without compromising performance. So the title Beyond the Bulk is certainly evoking that we will talk about surface characterization and why I think that surfaces are the big forgotten link in the chain of cement hydration and reactivity, but also beyond the bulk in the sense of moving away of the bulk of thinking and the big trend line on the way that science is done in the domain and what things can we do, new emerging techniques to understand better this phenomenon. So in any talk, that covers supplementary cementitious materials, I need to start by addressing the environmental aspect of it. And to do that, there are several ways of doing it. We could quantify and talk about the 7 to 8% of the anthropogenic CO2, right? Like the typical first two sentences in every paper in this field for the last 15 to 20 years. Or we could look at material stocks. This is an article that we published recently in Nature Communications, where we quantify the material consumption, and we can see the dominance of concrete in terms of mass and volume, making 90% of all the materials that are used in construction. And of those, 75% is concrete or cement-based materials, right? Mortar, renders, and concrete. So it is an absolutely dominant material, but also as we see here in this graph, it is very clear that despite the dominance in terms of mass and volume of concrete, in terms of CO2 emissions, we are actually quite efficient, right? Which is also something that is important to keep in mind, that going from this quantity to this type of consumption, as to compare to what steel is doing it, for example, is quite remarkable. But we certainly need to do better if we aim to achieve a decarbonized or carbon zero industry by 2050. The other aspect that is very important and that I want to highlight at this point is that several strategies for the decarbonization of cement and concrete have been put forward over the years. And I think that by now there is consensus that the most effective way of decarbonizing this quickly, at least in the time frame from here to 2050, which is not a long time left that we have, is to use low carbon materials or mineral additions to reduce the clinker factor in our cements. And this is something that we have been doing already for decades, right? There are the usual suspects like slag from blast furnaces and fly ash. But the problem is that many of these materials are not available in the quantities that we need them to replace, let's say, 50% of the clinker in our cement considering current demand. And why 50%? Because that's the estimation that the GCCA established for clinker factor to achieve carbon neutrality by 2050. And this is where these emerging, if you want, supplementary cementitious materials like calcine clays and limestone start to occupy a big role because they are highly available and they are in general cheap to obtain for cement producers. Now, what we have available in the crust is clay, is not calcine clay. There is still a gap that we need to fill with investment and with industrial adoption in order to make that clay resources that are available in the crust into reactive and processed calcine clays that we can use. And what make calcine clay so interesting is really the reactivity, right? So this is something that we can measure with a standardized method like ASTM CAT97, and we can see that overall calcine clays, in this case CY, are way more reactive than the other materials, and down the line that reactivity translates in the ability we have to reduce clinker further without compromising performance. And I also want to highlight at this point that the overall discussion of supplementary cementitious materials is twofold. So on one end, there is the decarbonization of the cement and the concrete industry in places where the clinker factor is still too high compared to their comparative, regions of income. And the US is certainly in that case. We have a higher average clinker factor than Europe. However, the global north in general, where the US, Europe, Japan, Canada, and the developed world in general is not the main consumer of cement. And it's also important to realize that on a global problem like global warming, we need to look at where the problem is actually going to be and develop technologies that are usable and implementable in those markets. And we know that the main consumers of cement in 2050 is going to be coming from China, India, Latin America, Southeast Asia, and Africa. So we have a responsibility setting an example, and we have a responsibility given the resources available in the global north to develop technology and solutions. But there is no value if these solutions cannot then be implemented and used in these other markets. If what we are aiming to do, which is at least the inspiration of my group at UC Berkeley, is affecting change at a global scale. So with that, being said, as introduction, I would like to move to the core of my presentation, which is to start a discussion on supplementary cementitious materials and reactivity, this word that we use so commonly, but many times without a clear definition, reactivity, and how we are pursuing performance in that way. So before moving to that, I thought that it was useful in a webinar like this one to make at least a reminder so we keep it present during the talk on how cement works, where we are coming from, and because these conditions, some of the things that then we deem as desirable in our material properties when we want to maximize things like reactivity. So the way that cement works is that we have a group of hydraulic phases in this material that we call clinker. We combine that with a little bit of a sulfate carrier and water. These grains of cement are going to dissolve, and this dissolution is going to put ionic species in the water, which is not going to be water anymore. This is a solution that we call the pore solution. And at a certain point in time, we are not going to go into detail on that in this talk in particular. We are going to meet a certain thermodynamic condition of supersaturation that will trigger a process of nucleation and growth of new solids that we call hydrates. And the magic of the process is that these hydrates that form incorporate part of the water from the pore solution into the solid, increasing their volume. So the hydrates are 2 times larger on average than the anhydrous materials. And this is the whole process of going into something that is a colloidal suspension into a load-bearing solid, right? These solids are growing in volume. They're able to impinge one to each other, and we originate this magic phenomena that cement has that we call setting. In modern cements, things get a little bit more complicated than this scheme, though, because in addition to clinker reaction, which in general, from a kinetic standpoint, we can deem as a fast chemical reaction, we have the chemical reaction of all of these mineral additions or supplementary cementitious materials that we may want to add into this blended cement to reduce carbon footprint that are in general slower. And it's important to realize that all the reactions, all the chemical reactions that take place follow this same pathway of dissolution and reprecipitation. However, the kinetics are different, and in many cases, reactions are coupled one to each other. For example, a pozzolanic reaction cannot take place until we have a sufficient amount of alkalinity in the system in order to get that pozzolanic reaction going. So there is a hierarchy that needs to be respected in how these processes take place over time. So what do we mean by reactivity? And I added this slide because I was inspired by a recent discussion with colleagues in Europe, and I realized that they make a very good point, right? That sometimes we talk about reactivity and we haven't necessarily agreed in the cement community. What do we mean by reactivity of an SCM, or what do we mean by reactivity of cementitious materials? So in general, if we take the UPAC definition as a basis to start, reactivity is a kinetic property. So it evolves over time and is established for a set of conditions. In general, reactivity in chemistry is defined for a specific elementary reaction. And in some cases, UPAC also recognized that the term can be most loosely used to describe coupled chemical reactions, or a more phenomenological description, as they called. And in those cases, it may reflect not only the rate, but equilibrium constants and other parameters, which is something that we are more familiar in cement science. So when we try to apply this to our case, we need to realize that in cement hydration, no reaction is single step based on the mechanistic definition that we just made, because we have at least dissolution and precipitation and growth involved in the formation of every hydrate. We have different coupled reactions that occur simultaneously. For example, all of the hydraulic reactions of clinker and the pozzolanic reaction or reactions of the different SCMs that we have in the system. And in most cases, we cannot access thermodynamic parameters of one reaction independently from others. And a clear example of this is possibility is what we use when we try to apply what the so-called maturity method in concrete technology, where we use this parameter, which is an apparent activation energy. Well, it's called apparent because that's not the activation energy of any of the reaction that happens, but in a sense is something that couples that group of reactions happening all at the same time. So for a chemist, this number actually doesn't represent much, but for us is what we can do considering that we have coupled processes occurring simultaneously. From a testing perspective, this is likely one of the areas where more progress has been made in the last 10 years, and we have developed methods like ASTM C1897, the so-called R3 test, to provide a rapid and reliable way of measuring or qualifying the reactivity of a supplementary cementitious material independent of the cement that I want to use it afterwards. So essentially what we do is that we make the SCM react in an ideal or an idealized pozzolanic environment in excess of portlandite and alkalis and sulfate in the pore solution, and we then obtain a certain value of heat evolved in the case of the calorimetry test, and we can compare that with compressive strength. And what we have seen, why we like this method, is that there is a pretty strong correlation between the heat evolved during the R3 test or the ASTM C1897 test and the compressive strength that we can measure in a mortar, at least better than what we observe with other competing tests like strength activity index or calcium hydroxide consumption. And I want to stop talking about those as well, like the competing tests, if you want, that we have to qualify and benchmark supplementary cementitious materials, because despite the ASTM C1897 being a more sophisticated test, the information that is specified in the standard is that we extract a certain heat value from the curve at a certain hydration point, 7 days, 3 days, 24 hours. The standard says 7 days, between 75 minutes and 7 days, but you pick your poison. Let's say you can look at but we are looking at a snapshot on the reactivity, and we know that the definition of reactivity involves this kinetic evolution or this time evolution that takes place. So we are explicitly excluding that by taking this snapshot, and the strength activity index and portlandite consumption are doing the same thing. We are looking at a moment in time and taking a picture of the reactivity, which is something that in general we like to do in concrete technology because we have ongoing reactions that make the properties evolve over time. So we take this snapshot in order to capture what's going on at a certain period of time. But it's important to keep in mind that this snapshot is not a representation of the reactivity. Actually, the reactivity considers this evolution over time, which we capture with the R3 test. It's just that that's not part of the value to be reported within the standard test method. And on this, I would like to now move to discussing the issues and the challenges that we have in cement science for relying so much on physical models in order to measure properties that for other domains are very simple, and the kind of mistakes that we can make by over-inferring or over-interpreting results that derive out of these physical models. And I want to make my point talking about two parameters that I believe for engineers or for anyone actually retain a very logical sense. For example, when we talk about particle size, if particles were macroscopic, I could imagine that should be able to pick up a ruler, go and measure this particle, and maybe the particle is going to be regular, right? But I can measure the minimum and the maximum diameter and calculate an average, or I can even, interpolate a geometric spherical equivalent diameter on this particle, whatever approach you would like to choose, but it's a geometric magnitude. It's very logical what we are trying to do. However, what we actually do in cement science is that we use laser diffraction and then we use Mies theory, which involves resolving this indefinite integral function where the size, r in this case, is part of the function, which is in complex variable, by the way. And when we measure particle size distribution using laser diffraction, actually what we are doing is finding, by guessing iterations, a solution for this indefinite integral. And we take several shortcuts in order to be able to find a numerical solution for this. We assume spherical particles. We have to assume a refractive index for the media and for the particle. And again, this is in complex variables, so there is a real and an imaginary component of it. And we are also assuming that we are taking good dispersion of these particles. So even things as simple as particle size can get complicated in cement science because of the sizes that are involved. Another one that I would like to mention is surface area. And similarly as particle size, we can imagine surface area as something where we have like a logical geometrical interpretation of what we are doing. If the particle was macroscopic, I should be able to go with a ruler or with a metric tape, measure dimensions, calculate areas, and then estimate what is the exposed surface of a certain material. However, what we do in cement science is that we use absorption isotherms. So we assume a monolayer or a multi-layer surface coverage of an adsorbent with an adsorbent, as we are seeing here for a silicate surface, much simpler than the materials that we work with regularly. And then we obtain this absorption and desorption isotherm. Luckily, we had this very smart group of scientists back in the past, Brunauer, Emmett, and Teller, that realized that rewriting the equation for this isotherm in a smart way, which is this representation here, this isotherm equation could be linearized. And this is what we call today the BET model. However, there is a bunch of assumptions that are being taken in this model, particularly that there is no chemical interaction between the nitrogen, in this case, and the surface, and also that we have a monolayer coverage, and that's why we only use the lower part of the isotherm where we have a really linear behavior. However, the issues arise when we start trying to compare the measured surface area by BET with things like reactivity, and we see that in many cases there is no correlation. And I would like to highlight that with an example. So we took this metakaolin, so these are experiments that we did in my lab, and we measured this metakaolin sample. We are not going to go into details on which specific metakaolin, but let's call it material A. And we measure the specific surface area by nitrogen absorption applying the BET method in the lab as 13.2 square meters per gram. Well, now we have other techniques like inverse gas chromatography that allow us to obtain absorption isotherms with a bunch of other molecules that are not necessarily nitrogen, as in the case on the typical device that all of us may have in our laboratories. And the interesting thing here, when we try the same metakaolin sample with two new gases, pyridine and isopropanol in this case, is that the surface areas that we obtain can be up to 3 times the value that we obtain by nitrogen. So in a sense, we cannot neglect the influence or the interaction between the adsorbate and the adsorbent in this analysis, because while the assumption for nitrogen may stand true for classical cementitious materials, in many cases, the chemistry of the surfaces of these emerging SCMs is such that those interactions cannot be neglected anymore. I added this molecular cross sections here because what many people assume here is that the reason why these surface areas change in values because the molecules are larger or smaller, so they start occupying more or less space over the surface. But actually you can see that it doesn't follow the trend because pyridine is actually larger in cross section than nitrogen, and still we measure at a higher surface area. So it's really a chemical interactivity process going on here rather than geometrical space occupancy. The other aspect that I would like to bring up for discussion is that many of the techniques that we use today to characterize our cementitious materials are what I call surface biased. And sometimes we forget this. This is common knowledge. However, some of these techniques have become routine for us, and we do it in such a systematic way over and over in our laboratories that we forget that these techniques in one measure or another are surface bias, and what we are sampling is only the surface of our material. So for example, laser radiation, which is what we use for Fourier transform infrared spectroscopy or Raman spectroscopy, a laser penetrates a cementitious materials 0.5 to 2 micrometers. So if I have a particle that is 20 to 50 micrometers, I'm really only sampling the surface here, and that's what brings information back to my detector. X-ray diffraction penetrates a little bit more, 10 micrometers, but still not a lot compared to the size of these particles sometimes. An electron beam in an SCM in a typical configuration for EDS, 15 kilovolts, would penetrate 1.5 to 3 micrometers. So if I have a particle that is 20 micrometers, 50 micrometers, I'm really only skimming the surface with this analysis. On the contrary, we have other techniques that are a little bit more bulk oriented, if you want. One of them I would say is isothermal calorimetry. For example, the R3 test or ASTM C1887. We have to be careful here because the initial kinetics are in fact driven by the surface. However, in this kind of system where we can achieve 100% degree of reaction, we can assume that at these higher levels of reactivity, the bulk start playing a role. And we have other techniques, and this is, at least for me, the biggest argument to work more and to do more in our domain with nuclear magnetic resonance is that this technique is actually a true bulk technique, right? It doesn't have this penetration issue that other techniques has. It just samples all the material, all the nuclei that are within that rotor and return information back. And I think that many of the discrepancies that we see in the published literature between the classics that we have on the left and the not so classics that we have on the right are in many cases stemming from this surface bias that is not accounted for when the experiments are conducted. So most techniques we use today to assess structural changes in supplementary cementitious materials are surface bias, and therefore that's why I think that coming back and making a point on surface characterization is essential to understand the so-called reactivity emergence on supplementary cementitious materials. So I want to talk a little bit more about calcs and clays, which is a big portion of what we do in my group. So before moving to calcs and clays in particular, a brief introduction on clays. Clays can be minerals of different groups. In general, we are more interested in the clays of the kaolinite family, or one-to-one clays, where we have one aluminol sheet per one siloxane sheet. That's why we call them one-to-one. And the particularity of this is that then the aluminum and the silicon is exposed through the interlayer space, whereas in 2-to-1 clays, we only have silicon exposed to the interlayer place. And that has an effect on the dissolution kinetics of these materials. Again, surface is the difference. It's really not just the bulk. Now, it's important as well to realize that these materials have a layer structure at the lattice level, but they also have a habit of precipitating layer crystals. And in order to distinguish these two, we are going to call in this presentation layers to the lattice units, and we are going to call platelets what we see, for example, in an SCM. And of course, the unit cells are oriented within these platelets, but they are not the same thing. One platelet thickness may have hundreds of stacks of these unit cells all pointing within the same direction. In general, we have the z-axis pointing towards the short axis of the platelet. So going back to inverse gas chromatography, this technique that I was describing before, this has been transformational for us because for the first time is enabling us to access surface properties that before were mysterious or a black box in terms of what relation they could have to the reactivity or to the emergence of reactivity of one of these materials upon processing, for example, in the case of calcined clay. So one of the things that we can measure with IGC is the dispersed component of the surface energy of gamma SD. And what we see here is that by using branch, linear, or aromatic molecules, we can access different aspects of the surface and get an idea of what it's called nano roughness of the surface. And what we see is that upon dehydroxylation, the nano roughness decreases over the surface at the atomic level. So for the first time, this technique, inverse gas chromatography, is allowing us to access features of the surface that for other techniques like SCM are not observable. I challenge anyone in this seminar to tell me which one is which out of these two micrographs without me telling you that this is kaolinite and this is metakaolin, right? So this is really happening at the layer level, not at the platelet level, coming back to the definition we just made. And on this, there's been this idea or concept that metakaolin content is a good predictor of reactivity, and that we can use the kaolinite content of a clay to relate to the potential reactivity that that material will have. And the answer is that in general, that works, but here go a couple of exceptions. Look, for example, from the original R3 test paper, that these two curves are reversed. So the one with the lower kaolinite content actually exhibits a higher reactivity versus the other one. And things that we have seen in more recent studies, when we have materials that have 30% more metakaolin than the other one, calcine under the same optimal conditions. However, when we see the total heat evolve in the C1897 test, these numbers do not necessarily correlate with that metakaolin content. Going a little bit more in depth, here we have two materials with essentially identical chemical composition and mineralogical composition that are both pure metakaolins. However, they exhibit a 35% difference in the reactivity. And let's go back again. Surface properties matter. What the XRF and the XRD pattern are telling me is a little bit more of an idea of what's going on in the bulk or on the close surface semi-bulk status. However, there may be difference here that these techniques are not capturing that have to explain this 35% difference in reactivity. It's clearly not a surface area difference as we see here measured by BET, nor something that we can detect by solid state NMR either. So it's quite puzzling to have these two materials with such a different reactivity, essentially exhibiting the same bulk chemical composition. So not trying to scare anyone about calcined clay here, but just trying to highlight that there is still a lot of things that we don't fully understand in terms of SCM chemistry and where is reactivity stemming from. This is the work of one of my students right now. He's producing synthetic clays in the lab by hydrothermal aging. And one of the things that we could do was to introduce doping of minor additions of iron in these clays. And he was actually able to reproduce this 35% difference by including look at the number, please, 0.15% iron in one of the starting materials. So again, these two materials have the same XRF. They differ essentially in 0.15% iron addition in one or the other, the same kaolinite content, the same specific surface area, and still have 35% difference in reactivity. So we need better understanding on how lattice defects and composition of kaolinite can influence the overall reactivity of metakaolin under equal activation conditions. The last point of my seminar for this morning is some thoughts on what I call the elusive question or the metakaolin reaction onset. And we have had evidence for a while now, this paper is from 2021, that metakaolin is very reactive, right? So we can record using classical experimental techniques calcium hydroxide consumption as early as 24 hours. But then the question is, how much earlier than 24 hours that reaction actually became significant, and can we assign metakaolin a role in things like sulfate requirement or superplasticizer consumption and demand for workability given an accelerated pozzolanic reaction? So the problem here is that measuring the degree of reaction of an amorphous material like metakaolin is challenging, and there are several ways of doing it, and all of them have disadvantages. So this is a paper we published in 2022 using a methodology called mass balance, and when we use mass balance, we obtain for different clays that we sampled a degree of reaction of 40 to 50% at 90 days. The other way of doing this is by 29 silicon nuclear magnetic resonance. So this is a methodology pioneered by the group of Jørgen Skibsted in Denmark. And with that technique, we obtain about 65 to 75% degree of reaction. So actually higher than mass balance. And we think that the reason for that has to do with the signal to noise ratio in those experiments. It's actually quite difficult to detect the metakaolin after the degree of reaction has evolved beyond, let's say, 50%. So my PhD student has been working in the last 3.5 years developing this methodology using isotopically labeled metakaolin. So this is a material that he produces where we can get 40% enhancement of the NMR signal, and hopefully by doing so get a much cleaner and much higher resolution on the evolution of the reaction of metakaolin in a cementitious system. And one of the things that he have been able to do by tracking this reference to degree of reactions determined using isothermal calorimetry is that we do not have a significant formation of pozzolanic, if you want to call it somehow that way, pozzolanic CSH before point D or E in this analysis, which is roughly the top of the acceleration period of halfway through the acceleration period. Setting occurs before that. Therefore, the argument that we are making is that our experiment is showing that there is no clear evidence of the reaction of metakaolin having an influence on the slump loss of the system, at least not from a chemical standpoint. The other thing that has been very enlightening from this is that by doing CP analysis cross-polarization, where you transfer magnetization from protons into the nuclei of interest, in this case silicon, you can see which silicons are neighboring protons, and we can see actually that the dissolution of metakaolin occurs from this left side of the hump, which is the side that we believe is closer to the surface. Last but not least, so this is the work of one of other of my PhD students using transmission electron microscopy. So what he is doing is looking at fully dehydroxylated and partially dehydroxylated kaolinites. And what you see here is what's called a Bragg vector map, where we average all the electron diffraction patterns that we collect over a certain area. So each of these plots contain about 1,000 diffraction patterns, individual diffraction patterns, and it's a probabilistic representation where red means that there are more, pixels on that, and green or blue is less representative. And what we see, as we would expect, is that as we progress in the dehydroxylation and amorphization, we start losing this point pattern that we see for well-ordered kaolinite, and we start seeing something that is more like a rim pattern, which is evidence of an amorphous material. Now, we can always index this, and what we do is that for each of these diffraction patterns, we try to index it to the known crystalline structure of kaolinite, and then we try to calculate a statistical cross-correlation parameter that tell us how similar the diffraction pattern is looking as to the ideal crystalline structure. So a higher correlation would mean that the material is very crystalline as compared to the structure file. A low correlation would mean that we don't have a lot of similarity between the electron diffraction pattern and the structure file. So, of course, you would imagine that kaolinite has a very high correlation because what we see experimentally is very similar to the structure, whereas metakaolin, that correlation drops to about 2 to 4, where here we have around 20 to 25. What is very interesting, and I won't say much about this, but I just want to motivate critical thinking about this, is that what happens in between, right? While we're moving from kaolinite into metakaolin, you would imagine that this peaks moves all at once from this 20 value until it reaches this 2 to 3 value that we see from metakaolin, that it moves towards the left in this case. However, what we see in between is that rather than having a single population, we start seeing this kind of bimodal distribution, indicating that the degrees of amorphization may not be as uniform within the space as we thought in the beginning. So to conclude, we need robust understanding of surface properties of metakaolin and SCMs in general. And this is something that is still missing. And I would like to encourage people working on this domain, PhD students, to pursue science, to revisit techniques, to revisit the fundamentals, because we need more work on this. The fundamental understanding will likely contribute to more robust prediction of potential reactivity compared to current anaperimetric indications, of which ASTM C1897 is still one of those. Synthetic clay minerals enable a new portfolio of experiments, particularly in terms of labeling, but also in terms of the lattice inclusions that we can now control, crystallinity and morphology. And we have seen, hopefully, publishing very soon, very, very interesting results with our labeled samples in the NMR. Preliminary results also show no substantial evidence of pozzolanic CSH precipitated during the acceleration period in the systems that we have studied. So I think that that's still an open question on is metakaolin really starting to react, explaining the quick slump loss that we see on these cements, or is there something else, once again, surface mediated, that is taking place and that is explaining the changes that we observe? So with that, I would like to conclude, and I would be happy to take questions during the remaining discussion time that we have allocated. Thank you very much.
Thank you so much, Professor Franco Zunino, for this great presentation. So now we're going to have a Q&A session for the remaining of the time. You guys can send your questions. We have a Q&A box, but if you don't find it, because sometimes it's a little bit hidden, there you can also send like a chat message with your question, and Professor Zunino can respond to your questions. Yeah, let's see if take your time to send the questions and we'll have to answers. Yeah, let's see. Okay. Yeah, we have a comment from Christina Leonelli. Great presentation. Thank you for sharing your research results and objectives. Yeah. Yeah, no, this was a really great talk, Professor. Thank you so much. I was very interested, was very interesting this technique. I wasn't very aware of this, of the measuring the surface properties with the different media. Can you actually have characterization of this, potentially have characterizations of not only the surface area, but let's say on the different absorption or characterization the actual surface of the different materials? Yeah.
So I think that what IGC brings to the table is the ability to increase this absorbent interaction from one, which is what we have in the lab with nitrogen, right? Like one gas that we always throw on top of our material, to, a typical good IGC battery measurement maybe tries 10 or 15 different gases over the same sample. And each of those gases is going to trigger a certain interactivity curve. And the power really starts when you start comparing those and looking at the molecular properties of each of these molecules, where you start seeing features in the surface that perhaps were not obvious at the beginning. Just an anecdotal fact, we did a very extensive um, inverse gas chromatography study back in 2018 of a lot of clays. We spent a lot of money doing it. And I never published it because I could never understand the result that I was getting. I look at this PDF with data for 5 years and it never made sense at all to me. It contradicted everything. It only made sense maybe 2 or 3 months ago in light of a completely unrelated piece of work that one of my students is putting together. And it clicked and it was like, oh, wow, that's what it is. So sometimes I think that the challenge of these techniques is that the interpretation is not ready or at a point where we can easily extract information that is industrially pertinent. But certainly, from a research point of view, the potential is insane. And I was looking at one of the questions in the Q&A, right? So somebody's asking about the BJH theory, which is another model that can be adapted to absorption isotherms with nitrogen. It is very useful, but it's also sort of a black box if you do not consider the non-negligible amount of assumptions that need to be taken to get there. So I think that from a porosity characterization, especially for SCMs that have porosity, like clays or natural pozzolans, is very useful. But it also has limitations. At least in the devices that we have in the lab, you cannot pressurize. So the maximum relative pressure of nitrogen that you can achieve is 1. So P over P0 equal 1. That means that for a BJH interpolation, you can achieve pore sizes of around 300 nanometers, which is not nothing, but it's likely a little bit too small still for some of the things that we may want to measure. So I think that there is still a place for complementarity between um, nitrogen absorption with BJH methodology and MIP or DVS and other techniques, right? It's one of the big pendings. I think that we do not have in cement science a good technique to measure porosity. They are all bad in their own way. And that's why we have to use all of them. But they all rely on big assumptions and they all have very high sample preparation bias. Um, there's another presentation that says, which technique would you consider the most reliable for the measurement of specific surface area? Based on what we have seen, none of them. There is really nothing that is unbiased. I mean, certainly nitrogen absorption provides a relatively clean measure, but as we saw, uh, depending on the surface, if you have a complicated surface, which unfortunately is the case with SCMs, I think that something that we are going to have to accept is that the chemistry of cement is getting more complicated as we move towards blended cements. SCMs are chemically more challenging than clinker. We understand it way less. We don't even have a structural model for metakaolin. We doesn't know how it looks like in space. So it's at that level of ignorance that we are at the moment. And I think that from a procedural point of view, we can continue using BET based on nitrogen absorption. However, it's important to always keep in mind that there is a bias, that there is a possible interactivity between the surface and that sorbate that may change the values that we measure significantly, as I try to illustrate, that you change the gas and you get 3 times the surface with exactly the same material. Um, There is another question that says here for the flash calcine versus the 800 for 1 hour. I guess that the static one. Do you think hitting a longer duration could reorganize the disorder in coordinate structure? Uh, we haven't seen indications of that. What I think that this is more, I don't think that this is a problem of heat transfer, which is I think what you're trying to hint here, that if you heat for a longer period of time, you're going to be able to warm up the center. Or this is what I understand that the person asking is trying to mean, right? I don't think that that's the problem. I think that for the sizes of samples that we have, compared to the size of the oven, uh, that heat transfer happens automatically. This is probably more thermodynamically driven, and breaking some bonds is probably not the same tax price as breaking others, and therefore, depending at which temperature you heat, you break ones but not the others, so to speak. But it's not that you have to spend a lot of time propagating this. Of course, in the distinction between flash and the other one, it's quite an extreme. So in that case, there may be a kinetic effect, but in general, I don't think that heating for a longer period of time is going to introduce any annealing in the system. Now, it could be interesting to look at it, right, and maybe lead these samples for a longer period of time, and see if there is any surface difference that we can detect. There is the fact that I don't know the answer, I think that should highlight that there is still a lot of things that we could do to try to get a better perspective on what's going on, and maybe we find something that could be useful. Have you investigated crystalline size as a way to distinguish amorphous and nanocrystalline contribution to SCM reactivity in R3 and LC3 system? If so, what size do you consider effectively amorphous? Okay, so that's a very interesting question. In the case of metakaolin, and I'm going to use that as an example, but I think that it extends to all amorphous SCMs. I don't think that we can speak about crystallites. In cement science, there is sort of an agreement, which not necessarily agree with, but it's a problem of scale. So it depends. That CSH is amorphous. Uh, Metakaolin is more amorphous than CSH. So, in other words, there is more disordered in an amorphous SCM than metakaolin, or the radius of, depth of short range ordering is at least 5 times lower in metakaolin as it is in CSH. So I don't think that the concept of crystallite applies. However, there has to be something going on that explains how 15 percentile points, so 0.15% difference in chemical composition or lattice substitution of aluminum by iron explain a 35% drop in reactivity. So, but I'm not necessarily sure that that's mediated by a change in crystalline size, only because of this argument of the structure being so disordered. That's something that we can quantify by PDF analysis, total scattering experiments. We don't see, even compared to CSH, this look disorder. And that's where the challenge of deriving a structure for metakaolin is going to be more difficult than CSH, because CSH has more order than metakaolin, and that's why it's so difficult for us to come up with a structure. Then Christina says, what do you think about the availability of volcanic ash as natural pozzolan in the cement consumer countries? If it's available, we should be using it. And that's why we need more people, and ideally local groups working on this, because we can't analyze every single zeolite or volcanic ash that there is out there. And I think that each market needs to understand their material. And at the end of the day, I strongly believe that it's going to be a portfolio of SCMs that we are going to have available, and that each regional context is going to make more sense than the other. Of course, calcined clays offer a reactivity that most natural pozzolans cannot achieve. And therefore, for special applications, it might even make sense to move calcined clay from one place to the other in order to produce this high performance cement. But for lower demand applications, I think that there is no reason why we cannot exploit local resources, why we cannot exploit local deposits of materials in order to decarbonize cement. And I would like here to put the example of the Chilean cement industry. I'm native from Chile, as some of you may know, and Chile has been using natural pozzolans, volcanic ashes, essentially, for, I mean, 80 years already at 40% replacement. No, not for sustainability. I mean, it's not we were not talking about carbon C and CO2 footprint 80 years ago. It's really because we don't have limestone in the country, and it's very expensive to produce clinker. So the only way to keep the price of cement in check was to use high substitution level of SCMs for a long period of time. But that built a lot of experience. And I think that the example that I'm trying to make here is that Chile is also arguably the most seismic country in the world, with one of the best seismic performances in the world. And that clearly show that good quality concrete can be made with SCMs at high substitution that exhibit, discrete or moderate reactivity compared to what a calcined clay would do. It's not a matter of concrete mixture design in the end. There's another question here. Any chance or point or gap with trying to use contact angle goniometry for these investigations? Thanks. Definitely an interesting point. The problem is how to obtain surfaces that are clean and oriented enough so we can get data that we can use beyond a qualitative observation. So the problem of all of these micro techniques or all of these techniques that we try to import from material science into cement science like right away is that the heterogeneity of our materials completely kills any chance of using the data quantitatively or achieving modeling capabilities with the data. So I think that the first step would be to be able to produce surfaces that are suitable for that kind of experiments. And I think that um, this is my personal opinion, and of course it's coming from very close, so take it with a pinch of salt, but I think that we are nailing it with our synthetic clays because can produce oriented platelets, and we can put the silicon or the aluminum atop however we want, and we can make it grow on any size that we want because we are precipitating, we are playing to be the earth crust on this. And then we can use that oriented surface for certain experiments. But I think that translating that into the other materials would imply a development or a material sample preparation procedure in the same order of complexity if the goal is to obtain quantitative data. There are two more questions, one in the chat and one on the Q&A. So I will go with the Q&A first. If you had to choose, which SCM would you prefer? Calcined clay or volcanic natural ash to make a high-performance concrete with long durability? Hypothetically. So if I can have both, I would pick calcined clay because it's just going to make my life easier, right? I don't need to think much. And at this point, I would be rather convinced to say that it's going to work no matter what. You even have some room to mess up a few things and it's still gonna work, provided that you get the workability that you want. I mean, that's a separate discussion, but I think that that's something that we can address nowadays with a little bit of concrete admixture technology. However, if the compromise of doing that is that I can only decarbonize a fraction of the market versus using volcanic ashes that are available, that are cheap, that are already paid for, let's say, and that enabled flat replacement of, let's say, 25, maybe not 50%, but 25% of the clinker throughout a market, as it happens in Chile, then I would do that first, and we use the calcined clays on top if needed to get higher performance. But I think that the biggest challenge that we have with calcined clays in the global north, this is not a problem in the global south, but in the global north, is that we are still in the process of rolling out and deploying more production facilities. But it should get better in the coming decades. I'm gonna move to the chat now. I wonder how critical sulfate optimization in LC3 is to control aluminate species in pore solution and to prevent potential silicate reaction interference due to the presence of masses aluminum in pore solution. It is important, but it is important for reasons that do not have to do necessarily much with the aluminum content. And I know that my answer gets confusing and probably merits a much deeper discussion about it, but the gypsum demand of a given cement has very little to do with the aluminum content of the system, although it's aiming at controlling the aluminum reaction. We have not seen a distinguishable higher aluminum in pore solution in, let's say, LC3 systems during the period where sulfate balance is important, which is before the aluminate peak. Why? Because all of that aluminum is being consumed to form metric. The aluminum concentration in the pore solution raises when you run out of gypsum, but not before. So it is important, but it is more important than anything to keep the aluminum reaction in general, not the SCM aluminum reaction, but the aluminum reaction of the clinker as well, to not impeach the reaction of clinker. But this is true not just for calcined clay, it's true even for PLC, for limestone. If you use a fine limestone with a small enough particle size, you are going to end up in the same undersulfation system as you would in an LC3, even though in that case you have less aluminum. That's what I mean with not having to do with the aluminum content at all, actually. Do we still?
It's up to you. It's your time. I'm
Yeah.
okay. But if you
Yeah,
want just to,
let's do this two last, and I think that
yeah,
then we're gonna call
okay.
it a day because yeah, people probably have to go and do other things. So beyond just reactivity, have you also seen any impacts from clay material characteristic or the hydration product matrix, different morphologies on the product basis on the clay parameters that could impact? No, we haven't seen anything like that. More importantly, I think that this distinction that some textbooks make between pozzolanic CSH and normal CSH is part of the mythology. So that's kind of like old way of understanding cement hydration. Is all the same thing. Everything precipitates through dissolution. So you can imagine that if everything goes to the soup, and then from the soup you get the croutons, which are your hydrates, it doesn't matter the origin of this stuff going into the soup. It doesn't matter who added the salt, the SCM of the clinker. It went to the soup, and then you pick from the soup what you need to form CSH and you put it together. So in a sense, the morphology is the same. What we do see though, from a compositional point of view, is that things like the calcium silica ratio and the main chain length of CSH is different in a blended cement, but that's explained by the composition of the pore solution actually, so it shouldn't be that surprising. And then there is a last question that says, thanks for answering my question. Why doesn't crystallite size applies in this case? Because I don't think that there is crystallites. I don't think that you have domains that are large enough to meaningfully call it a crystallite. So in the case of CSH, I think that we have crystallites. A crystallite of CSH is roughly 5 to 10 nanometers. So that's the order domain or the size of the nanofoil, as we call it. You don't even have that for what we have seen so far in metakaolin. Is more disordered than that. So there may be some degree of domains that repeat, but at least in the classical definition of crystallite, I don't think that that's the case in SCMs. At least metakaolin. Can the XRF XRD mass balance be used to optimize the amorphous phase composition? Yes, you can. However, in the way that we do mass balance, the composition of the SCM is actually assumed, is not an output. So if you want the composition of the amorphous phase to be part of your output, you likely are going to need another technique on top to be able to distinguish. I think that what would be easier in that case would be to do, you don't need to do mass balance in a sense. I think that you just need to do XRD, quantify the crystalline stuff that you have in the SCM, and then subtract that from the XRF analysis, and then you're gonna have an estimation of your composition of the amorphous phase. And if you want to overkill it, you can probably go to the TM, do diffraction first to check that that's the amorphous part, and then do EDS on it. But probably XRD and XRF are easier. And I finished the questions.
Okay, thank you so much, Professor Franco Zunino again. That was such a great talk, and thank you everyone for attending. You can stay in the call for a while, but thank you everyone. And yeah, bye. And make sure you respond to the survey, please, so we can get some feedback. Thank you so much, everyone. Bye. I know.